We've got a new letter today and a new task. Let's read it. The change in the state of a monatomic gas with a constant mass occurs according to the cycle shown in the figure. During the transition from state 1 to state 2, the gas performs work 5 kilojoules. Okay, let's write it down. Work from state 1 to state 2 is 5 kilojoules. And the question is, how much heat does the gas give off per cycle? Quantity of heat given. Okay, what we know, this task relates to thermodynamics. And what we know about thermodynamics? We know just the first law of thermodynamics, where delta means a change of something, U it's the internal energy of the gas, equals to Q. Q is a quantity of energy provided to a gas or a heat, minus work of a gas. Here it is work done by this gas. And there is another view of this equation. Let's write it down. Here is the same, delta U equals to Q, the same Q, and here is plus the work done on a gas by its surroundings. And here we see minus and here we see plus. Minus work of a gas and plus work done by surroundings of a gas. And I would recommend you to remember the first equation, because it's related to the gas. Delta U, the internal energy of gas, and work of gas. So let's go step by step. And the first step is transition from state 1 to state 2. From state 1 to state 2. In this case, delta U12 equals to Q12 minus work done by a gas 12. And here we know that it's 5 kilojoules. Hence, quantity of heat is delta U12 plus work 12. Delta means a change in the internal energy of our gas. So gas goes from state 1 to state 2, and the change of internal energy is U2 minus U1. Here we must write down the last state minus the first state. The last state minus the first state, number 1, plus work 12. So what is internal energy? Internal energy is N times R times T, where N denotes to the quantity of gas or a number of moles of a gas. R is a universal gas constant, and T it's a temperature of a gas in any state, in state 1, state 2 or state 3. And we must multiply this on 3/2, because this gas is monatomic. So if there are 2 atoms, then it should be 5/2. But monatomic, and it is dualatomic. We also know the ideal gas law. The ideal gas law is pressure times volume, and it equals to N times R times T. And here is the same, here and here. So in our case, the change of the internal energy will be, here is 3/2 times N times R times temperature of the second state, because here is the second state, minus 3/2 times N times R times T, the temperature of the first state, plus work 1, 2. And it is 3/2, and let's substitute the ideal gas law. In the second state, we know that it is 3/2 times pressure in the second state times volume in the second state, minus 3/2 times pressure in the first state, volume in the first state, plus work 1, 2. So in the first state, pressure is 2 times P0. Oh, sorry, in the second state is the same. And the volume is 3 times V0 minus 3/2. In the second state, it is 2P0 times the volume in the first state is V0 plus work 1, 2. We also know that in coordinates P, V, a work of a gas equals to the area under the plot. In our case, we have a transition 1 from state 1 to state 2, and a constant will be, let's shade the content. So we can see that it's a rectangle, and its area is one side of rectangle multiplied by another side of rectangle. So in our case, so let's write down 3/2 times 2P0 times 3V0 minus 3/2 times 2P0 times 1V0 plus, and there is another thing. If the direction of transition from state 1 to state 2 coincides with the direction of xv, then work will be positive. In other case, the work will be negative. In our case, we see that transition from state 1 to state 2 coincides with the direction of xv. So work will be positive. And work is an area of this rectangle. One side is 2P0 2p0, and another side is this segment, and this segment equals to 3v0 minus v0. So we see that it is 3/2 times 2p0. 3v0 minus 1v0 is 2v0 plus 2p0 times 2v0. And we can see that this is positive, a positive number, and in this case the system doesn't give off any heat at all, and somebody is heating our gas. So let's go to the second step, the transition from state 2 to state 3. State 2 to state 3. In this case, the quantity of heat will be state 2, state 3, will be delta U to 3 plus work done by the gas to 3. And we know that the change of the internal energy is the last state minus the first state. In this case, the last state is state number 3 and the first state is state number 2. So it will be U3 minus U second plus work to 3. So the internal energy in the third state will be 3/2 times N times R times temperature in the third state minus 3/2 times N times R times T, temperature in the second state. So, and let's talk about the work done by the gas in the transition from state 2 to state 3, and this the work will be the area under this segment, and we can see that this area is this trapeze. Let's shade it. So the area of trapeze is half of the sum of the first base and the second base. The first base is P0, it is this segment, P0, plus the second base. The second base is 2P0 plus 2P0 divided by 2, and we must multiply it on the height of the trapeze, and the height of the trapeze is this segment, 3V0 minus V0. And we must write down here minus. Why minus? Because the direction of xv doesn't coincide with the direction of the transition from point 2 to point 3. We see that the direction of xv is to the left, while the direction of transition from state 2 to state 3 is to the right. So they doesn't coincide, and this means that we should write down minus here. So it equals to, let's substitute the ideal gas law here, and we know that 3/2, in this case state number 3, it is pressure of the third state times volume of the third state minus 3/2 pressure of the second state times volume of the second state minus, it is 3p0 divided by 2 and multiplied by 2v0. So in our case, we know that pressure of the third state is P0 times volume of the third state is V0 minus 3/2 times pressure of the second state is 2p0 times volume of the second state is 3v0. Okay, minus 3p0 times v0. So in our case it will be 3/2 p0 v0, and here is 6p0 v0. That means that it is minus 1 minus 6 is 5. 5 p0 v0 minus 3 p0 v0. 3 times 5, it is 15 minus 15/2 p0 v0 minus 6/2 p0 v0. It is minus 21/2 p0 v0, and it is a negative number, and it means that in transition from state 2 to state 3 the gas gives off its heat, and if in transition from state 3 to state 1 the gas doesn't give off its heat, then this will be the answer of our task. And the last step, step number 3, in this case the transition from state 3 to state 1, 3-1. In this case the change of the internal energy 3-1 equals to the quantity of heat 3-1, and work will be equal to 0 as there is no content under this segment. There is no content under the segment 1-3, and in this case quantity 3-1, it is the change, the last state here is state number 1, internal energy in state number 1 minus internal energy in state number 3, and it is 3/2 times N times R times temperature in the state number 1 minus 3/2 times N times R times temperature in the third state. And it is, we must substitute the ideal gas law here, and it is 3/2 times pressure in the first state times volume in the first state minus 3/2 times pressure in the third state times volume in the third state. Okay, pressure in the first state is 2p0. It means that 3/2 times 2p0 times volume in the first state is v0 minus 3v0. Pressure in the third state is p0 times v0, and it is 3/2 times p0 v0, and this is a positive number. It means that our gas gains the heat from the surroundings, and it doesn't give off any heat. Let's get back to the question. The question is how much heat does the gas give off per cycle. So we see that in the transition from state 1 to state 2, the quantity of heat is positive. In the transition from state 2 to state 3, the quantity of heat is negative. And in the transition from state 3 to state 1, the quantity of heat is also positive. It means that quantity of heat in the transition from state 2 to state 3 is the answer of the task. And as we remember, it is 21/2 p0 v0. And we also know that work done by the gas in transition from state 1 to state 2 is 5 kilojoules. And we know that work is the content under this segment. The area of this rectangle, one side multiplied by another side. The first side is 2p0 multiplied by another side. It is this segment, 3v0 minus v0, and it is 2p0 multiplied by 2v0. It is 4p0 v0, and it means that p0 v0 is 5 kilojoules divided by 4. Sorry, kilojoules. And let's substitute 5/4 into this equation, and it is 21/2 times 5/4 kilojoules, and the answer is 13.125 kilojoules, or it is 13,125 joules. Okay, congratulations.